This video will discuss confidence intervals. In a general class, when I teach this, I generally show a video on the game of The Price is Right. If you've never watched The Price is Right, shame on you, you're missing out. But The Price is Right is a consumer-based game where they play these consumer games and they try to guess prices to different things and different items. But I show a video, and the video is called, the game that is played is called the range game. And in the range game, this lady, Linda, she tries to guess the price to a trip to Rome. And they allow her to play with this range of values. All right. And Linda has no clue what the price of the trip is, but they give her this range of values, try to guess it. She has to place the true price of the trip into the range. And so what we're doing here, and what I do when I show a video, is I'm trying to build what a confidence interval is. And in a confidence interval, it's an interval estimate. We call it an interval estimate. So far, what we've been working on is what we call point estimates. A point estimate is a single value. Such as if you try to find the mean of a value, if you're trying to find the mean of a value, you don't know it, you're going to use the sample mean. The sample mean is a point estimate. It's one value. What we're going to try to do now is develop a range of values or an interval of values to try to guess that price. And these values are going to be plausible values for some unknown parameter. So we're trying to guess the true value from our data. Our data is going to provide us with some plausible values. We're going to, instead of using one value, we're going to try to guess it with a range. And it's formed from taking repeated samples from the population and trying to capture the true value or parameter of interest. So the goal here is to repeatedly do this over and over again. And when you do this, you're trying to capture that true value, that unknown value. And we're going to develop this thing called confidence. And confidence is the percentage of samples that actually capture the true value using this method. So we're going to say we're like 95% confident. If you're 95% confident, that means that if you do this over and over again, 95% of your actual intervals would capture that true value. Or you can think of, if you have 100 intervals, only 5 of them would miss the true value. And the confidence level that we're going to do, we're going to find one for the mean. And everything's going to be based off of what we talked about in our earlier chapters, the normal distribution and the central limit theorem. And we're going to do this using these things called critical values. The critical values are going to be z-scores that are going to help us distinguish the plausible values from the non-plausible values. And remember, a z-score is just how far above or below the mean you are. So we're going to sit our mean in the middle, use these critical values to decide what values are plausible based on that, and what values are not plausible. And so here's how this is going to look. In the middle of this curve is going to sit our mean value, or for this particular case, we're trying to figure out what this mean value is for this curve. The only information we have available to us, though, is the sample mean, x bar, and it's going to sit right here in the middle. We're going to use this error. We're going to call it the margin of error. We're going to develop it eventually. But it comes from these things called critical values, or what we call Z-star. So Z-star sits here, and the negative Z-star sits here. They're symmetric to each other, so they're the exact same values. Just one is positive and one is negative. Our goal is to try to be able to fit whatever mu is, the true population. We want mu to fit somewhere inside of this region right here. And we're going to give this a confidence level. For instance, if this was 95%, then we would expect 95% of the time mu would fall inside of here. That means mu can fall somewhere over here, or it can fall somewhere over here, or it can be on the line here. But it has to fall inside of here. And what Z-star does is it gives us plausible values for mu. And we hope that those plausible values are close enough to the true value that we can use them. This right here is called the safe region. And it means that we expect mu to fall inside of there and it's safe. Anything falling on the outsides out here and out here, we're going to call the rejection region for mu. So we're going to reject those values right there if they fall in this region. Here and on the other side as well. And now, so we're going to go develop this value we call Z-star. And let's do a couple examples of how we find Z-star. And so here are some typical critical values that we can find, or confidence levels, what we're going to call them. These are confidence levels. Every confidence level has a critical value or a Z-star associated with it. And here's how we find that Z-star. If we say we're 86% confident, what we're going to do is based off the normal curve again. So we're going to draw a normal curve. And underneath this normal curve, we want the bounds for a Z-star. We always find the right-hand Z-star because the left-hand Z-star is a negative value. So we know the right, we can find the left. We want the bounds for a Z-star where 86% of this data is going to fall inside of here and be in the safe region. Well, here's how we find Z-star. We're finding area underneath the curve, and we're finding a value that corresponds to that. Remember, this is going to mean we need to use the inverse norm function. We need to use inverse norm. And remember, inverse norm is area and mu and some sigma. Well, because we're finding Z-stars or Z-scores, we know mu has to be 0 and sigma has to be 1. So the only thing we're really finding here is area. And in our calculus, we're not even going to touch the mu and sigma here anymore. Because if you don't touch it, it defaults to 0 and 1 mean, which means you're finding Z-scores when you find inverse norm. So we're going to go inverse norm and try to find the area. Well, here's how this works. If I want to find this Z-star right here, right now, how much data sits underneath this curve? 86%. How much is on the outside? Well, you have a total of 86 on the inside, so there's 14% on the outside. But there's only 7% here and 7% here. Well, we're trying to calculate up to here. So how do we calculate up to this value here? We're going to add everything in front of it, which if you notice is 86 plus 7%. So this is actually equal to, underneath this curve, what I'm interested in, underneath this curve up to this Z value is 94% of the data. That's 86 plus 7%. And so my calculator, I'm going to do inverse norm of 0.94. And that's going to give me a Z-star. So you do second bars, inverse norm, 0.94. And that gives you a Z-star of 1.555. And now we can do that same process to the rest of these. And here's how this works again. Let's do another one. So look at 90%. 90% says, draw a curve. On the inside of this curve, I want 90% of the data to lie right here. So I need to find this Z-star that corresponds to 90%. Well, how much is on the outside? Well, if 90% on the inside, there's 10% on the outside, but it means splitting up over two tails. So there's 5% here. So in the calculator, we're going to do inverse norm of 0.95. And if we do that, we get a Z equal to 1.645. And what that really means is that this Z star is 1.645. The negative Z star is negative 1.645. If you do in your calculator normal CDF, if you do normal CDF, negative 1.645 to positive 1.645, you're going to get 90%. And that's because 90% of the data lies between those two values. So that's what you're really trying to find is what two values do that particular confidence level lie. So 95%, which is a very common one. Draw a curve. And here you're going to split this into upper and lower regions. So you have a Z star here. And this time you want 95% on the inside. How much is not on the inside? 5%. Well, split up amongst two tails. That's 2.5% to this side. So when you add those up, 95% plus 2.5%, you get 97.5%. And in your calculator, you do inverse norm, 0.975. And you get a Z star equal to 1.96. The last one, 0.995. Again, draw your curve. And again, this time you want 99% under the curve. So if 99% is under the curve, how much is not underneath that curve? 1%. But you're only interested in, but you have to split that 1% amongst two tails, so you only have 0.5% sitting out here. So when you do this, it'll be inverse norm, 0.995. Because you have to add 99 to the 5%, so that's 0.995%. And you should get 2.576. if we look at all of these these Z stars, these critical values, what happens as the confidence increases? So you notice here, as your confidence level is getting wider, or as your confidence level is getting bigger and bigger and bigger, what's happening to the Z value? What's happening to the Z star value? Well, look, at 90% it was, or I'm sorry, at 86% it was 1.55. 90% it moved up to 1.645. 95% moved up to 1.96, and 99% moved up to 2.576. So notice, as the confidence is increasing, as your confidence, let's draw a curve and look at these. So as your confidence is increasing, 86% was like this. And then 90% moved out further. And then 95% moved out even further. And finally, 99% moved way out here. So as the level of confidence increases, what happens to the interval or the width of the interval? It also increases. So as your critical value, as your level of confidence increases, your critical value is going to increase as well because it's making your interval wider and wider and wider. And it's getting wider like that because in order to be more confident, when are you more confident? Well, you're more confident if that interval is wider because you're going to capture more because it's so wide. So keep that in mind. The wider, the more confident you are, the larger the critical value has to be. And it has to be larger because it wants to be a wider interval.